All right. So I'm going to talk about derivatives of exponential and logarithmic functions now. The slides I uploaded have a bit of a derivation of this, but the key thing that you should know is that if I take the derivative of the function e to the x, you just get the function e to the x back. If you take the derivative of the natural logarithm of x, you get 1 over x back. So that's the key. Those are the key facts about derivatives of exponential and logarithmic functions. And deriving this is sort of a tedious exercise in using the power rules and the logarithm algebra rules to simplify the difference quotient. Now, you can also take derivatives of other bases, but if you do that, what ends up happening is you get, so the derivative of b to the x is b to the x, but then it's multiplied by the natural logarithm of the base. So now up here, notice that the natural logarithm of e is 1, so if b was the natural exponential base, these definitions match. And so the natural logarithm, if instead you take the derivative of log base b of x, you're going to get 1 over x, but then that x is going to be multiplied by the natural logarithm of b. You just get this sort of factor because the base is different. And this one's actually easier to see. The log base b of x is log base b of x is the natural logarithm of x divided by the natural logarithm of b. So then that's why there's a natural logarithm of b in the denominator. And so now we've got these new derivative rules, so we can take some derivatives of expressions that we couldn't before. So for example, if I give you the function f of x is 7 times e to the x plus 5x squared, then its derivative, so 7 is a constant, the derivative of e to the x is just going to be e to the x. And then what's the derivative of 5x squared? Well, x squared is a power expression, so you're going to use the power rule. You're going to get 5 times 2x, and so you're going to get 7e to the x plus 10x. And now how about if g of x is the expression 4 to the x plus the natural logarithm of x minus the log base 7 of x. Then the derivative is going to be the natural logarithm of 4 times 4 to the x plus 1 over x minus 1 over x times the natural logarithm of 7. Now, a key thing I want to point out is that the derivative of e to the x is not equal to xe to the x minus 1. That's what you'd think it would be if this was the power rule. But remember, the trick is that x here is the variable. So if the variable is in the exponent, you're going to use this rule. If the variable is in the base, you're going to use the power rule. So a sort of dumb trick question version of this is if I ask you what's the derivative of x to the e. Well, x is the variable and e is a constant, so now this is e times x to the e minus 1. You apply the power rule to do this. So let's do another one. Let's find the equation of the line tangent to f of x equals 5e to the x minus x to the 4th plus 3 times the natural logarithm of x at x equals 2. So first off, f of 2 is 5e squared minus 2 to the 4th plus 3 times the natural logarithm of 2. which works out to 5e squared minus 16 plus 3 times the natural logarithm of 2. Now f prime, so the derivative of e to the x is again simply e to the x. The derivative of x to the fourth is 4x to the third. And the derivative of 3 times the natural logarithm of x is 3 over x. So that means f prime of 2 is 5e to the second minus 4 times 8 plus 3 over 2. So 4 times 8 is 32. This is 1.5. So you get 5e squared minus 30.5. So we've got the slope and we've got the coordinates. And so the equation for a tangent line is y equals f prime of, let's say, a times x minus a plus f of a. So in this case, that is 5e squared minus 30.5 times x minus 2 plus 5e squared minus 16 plus 3 times the natural logarithm of 2. And that's your tangent line.